Section 23, Cosmic Inflation. This section was updated March of 2025. We have now completed the timeline of the universe from a few trillionths of a second after the Big Bang to 1 billion years after the Big Bang. Next, we cover the first billionth of a trillionth of a trillionth of a second, 10 to the minus 33 seconds. There is physical evidence supporting the standard cosmological model back to the first second after the Big Bang, and even the first trillionth of a second. But there are three cosmology and physics problems that we will now discuss, and one assumed solution. In physics, the Planck time is 5.4 by 10 to the minus 44 seconds, a specific amount of time. In cosmology, the Planck time is the time 5.4 by 10 to the minus 44 seconds after the Big Bang, a specific epoch in time for our universe. At and before the Planck time, we cannot rely on general relativity, the Friedmann equations, or their results for expansion of the universe. Before that time, we need a verified theory of quantum gravity that merges general relativity and quantum mechanics, quantum field theory, which we don't have. Since we will be talking about the extremely early universe and cannot rely on our cosmological results before the Planck time, I will start referring to times after the Big Bang or Planck time. We could say nothing about the time before the Planck time. Later, we need to reference the Planck time. An assumption required to use Friedmann's equations for the expansion of the universe is that at any time, the composition and energy density is the same at all locations in the entire universe and in all directions, homogeneous and isotropic. One result will be that the radiation temperature would be the same at all locations and in all directions. We saw in section 19 that the cosmic microwave background has the same temperature in all directions to 30 parts per million, justifying the use of Friedmann's equations and its results. Also, astronomers believe our visible universe of galaxies seems nearly homogeneous and isotropic on a large scale today, greater than 200 megaparsecs. So, great, we're justified in using Friedmann's equations. What's the problem? The first problem is, why is the cosmic microwave background so isotropic? This is called the horizon problem. Initially, we might just say, well, it looks like our universe simply started with a single temperature everywhere and exactly zero fluctuations. Cosmologists and physicists don't like that answer, and cosmic microwave background fluctuations are not exactly zero today, so they could never have been exactly zero in the past, though they could have been quite small in the early universe. So then we step back and say, okay, let's assume that at some time in the early universe, the entire finite volume of our visible universe was extremely close to thermal equilibrium at one temperature, with only extremely small local temperature variations that grew relatively as the universe expanded, with expansion decelerating as radiation and matter energy density fell. But this gives us two new problems. In order for a volume to be in thermal equilibrium at some time after having previously not been in thermal equilibrium, there must have been a mechanism for bringing about thermal equilibrium and sufficient time to reach thermal equilibrium. These are a problem. So far in this course, we have assumed that radiation-dominated expansion in the early universe, starting with the Big Bang or Planck time. In this diagram, we are the blue dot at the center, here. The blue solid circle here is our present observable universe. The blue dashed circle within the solid circle is our present cosmic microwave background visible universe. The orange and purple dots are points currently 45 billion light years distant from us, 13,900 megaparsecs, at the edge of our visible universe in opposite directions. They are presently 90 billion light years distant from one another, 27,800 megaparsecs, and the present cosmic particle horizon distance, the present radius of anyone's observable universe, is 46 billion light years, based on what we've learned so far, 14,200 megaparsecs. The orange and purple points are almost twice as far from one another as the present cosmic particle horizon distance. If expansion of the universe was dominated by radiation, expanding but decelerating, from the Big Bang or Planck time until matter-dominated radiation at 50,000 years after the Big Bang, then the orange and purple points have never ever been in causal contact with one another. The purple point is beyond the orange point's observable universe, and vice versa. No signal, not light, not neutrinos, not gravitational waves, emitted from the orange point has ever reached the purple point, and vice versa. In that circumstance, there could not have been a process and time for the radiation at those 2 points to reach thermal equilibrium starting from non-equilibrium. There is no reason we should see their cosmic microwave background temperatures so nearly equal. Yes, the universe might have begun in perfect thermal equilibrium, exactly the same temperature at all points in the universe, but the cosmic microwave background has slight temperature variations. So that is the horizon problem. This problem would seem to go away if somehow magically our cosmic particle horizon distance would be much larger than we had thought it was, much larger than the size of our visible universe. Initially, we might think that doubling the horizon distance would be enough, such that the purple point would be within the orange point's observable universe at the present time. It turns out this is not enough. We need the purple point to be within the orange point's observable universe at the time of recombination and last scattering, and actually since the early universe. In this diagram, the large dotted circle represents our present visible universe scaled with the scale factor for last scattering at 370,000 years after the Big Bang or Planck time, 12.7 megaparsec distance. So that's the radius of the circle. It is not the size of the visible universe at the last scattering time, which is 0 because the cosmic microwave background is just starting to travel. The cosmic particle horizon distance at the time of last scattering is shown here as the radius of the 5 small colored circles, 0.257 megaparsecs. We need the horizon distance at the time of last scattering to have been at least 100 times larger for the opposite points, orange and purple, red and green, to have been within one another's observable universes at the time of last scattering, so that they were causally connected in the early universe and reached thermal equilibrium in the early universe, if somehow that could be. That is the horizon problem. At the end of this section, We will come back to those CMB temperature fluctuations. There are two other problems as well. Secondly, our observable universe appears to be nearly flat, near zero curvature today. It might perhaps be exactly flat, exactly zero curvature, and the universe spatially infinite. If curvature started exactly zero at the Big Bang or Planck time, then it would have remained exactly zero for all time. But if curvature is not exactly zero today, if our universe is finite in extent with positive curvature or infinite in extent with negative curvature, then the curvature value should have been much, much closer to zero in the very early universe if radiation dominated expansion and expansion was decelerating. Einstein's general relativity and the Friedmann equations allow a universe with any quantitative value of positive or negative curvature. Our universe could have started with exactly zero curvature, and perhaps it did. But if curvature now is close to zero but not exactly zero, why would our universe have started with some extremely small but non-zero curvature value when it could have had any value at the Big Bang? This is called the flatness problem. We saw in section 19 that cosmologists use the data from the cosmic microwave background, type 1a supernovae, and baryon acoustic oscillations to determine the present dark energy density on the vertical axis and matter energy density on the horizontal axis. Cosmologists have 95% confidence that the values lie within the dark ellipse at the center of this diagram, within this ellipse. The dashed line represents an infinite universe with zero curvature, flat, which could well describe our universe. Points above or to the right of the dashed line represent finite universes with positive curvature, the three-dimensional analog to the two-dimensional surface of a sphere. Points below or to the left of the dashed line represent infinite universes with negative curvature. For the purpose of this class only, I will invent the non-standard term flatness deviation, being the absolute value of 1 minus the total energy density divided by the critical energy density. 0 for zero curvature, a flat universe. Cosmologists have 95% confidence that the present flatness deviation is less than 0.005, 1 part in 200. When expansion is dominated by radiation or matter, expanding but decelerating, the flatness deviation increases with scale factor and time. The flatness deviation was much smaller in the early universe when the scale factor was very small. The flatness deviation would have been less than 10 to the minus 61 at the Planck time if radiation had dominated expansion since the Big Bang. Why should our universe have started with such a ridiculously randomly small value if it is not exactly zero? But the value matters a lot to our universe. If our flatness deviation had been 1 billion times higher at the time of Big Bang nucleosynthesis, our universe would have either ended long ago in a positive curvature big crunch, which obviously it did not, or we'd have a negative curvature big chill with no stars or galaxies. But we do have stars and galaxies. Our universe seems to have a special condition for flatness to have lasted this long and produce stars and galaxies. So, that is the flatness problem. There is one other problem as well. Physicists have never found an elementary particle with an isolated magnetic north pole or south pole, a magnetic monopole. If you took electricity and magnetism in college, you might remember that the divergence of the magnetic field B is zero because there are no magnetic monopoles. But theoretical physicists believe magnetic monopoles could have been produced in the extremely early universe, when the theoretical grand unified theory, GUT or GUT, period ended. When the strong nuclear force and electroweak interaction separated around 10 to the minus 36 seconds after the Big Bang, topological defects theoretically could have been created at that time and never created or destroyed thereafter. Those topological defects could have been magnetic monopoles, but might not have been. The apparent absence of magnetic monopoles in our observable universe is called the magnetic monopole problem. Well, perhaps they never got created. That could be. Physicists are not certain, and theories at that energy range can't be verified experimentally. Or perhaps the monopoles exist, but physicists have just not found them on Earth. It turns out the problem is bigger than that. If topological defects were ever created at all, even if they were not magnetic monopoles, the point-like topological defects are predicted to have had rest mass energy around 10 to the 12th tera electron volts, 6 trillion times the mass of the next heaviest particle, the top quark. A particle mass comparable to a bacterium. Expansion of the universe would have become dominated by the matter energy density of the topological defects beginning around 10 to the minus 16 seconds if radiation dominated expansion between 10 to the minus 36 seconds and 10 to the minus 16 seconds. That would not be our universe at all. Cosmologists are virtually certain that expansion was dominated by radiation, not matter, from a trillionth of a second after the Big Bang to 50,000 years after the Big Bang. And searches for magnetic monopoles give an upper limit to their energy density that is inconsistent with radiation having dominated expansion from the Planck time if they had been created. So, that is the magnetic monopole problem. Now for the solution to all three problems. In place of separate special conditions for flatness, homogeneity, and magnetic monopoles, around 1980, cosmologists proposed that there might have been an extremely short period, extremely early in the universe, when expansion of the universe accelerated and the scale factor increased exponentially by a lot, by at least 26 orders of magnitude in one scenario. Exponential cosmic inflation by at least 26 orders of magnitude in as little as 10 to the minus 34 seconds. Cosmologists call this inflation, cosmic inflation, cosmological inflation, or hyperinflation. There are different possible scenarios. We will look at one scenario: exponential cosmic inflation at constant energy density starting shortly after separation of the strong nuclear force and the electroweak interaction, shortly after creation of any topological defects has ceased, 10 to the minus 36 seconds after the Big Bang or Planck time, and ending abruptly at 10 to the minus 34 seconds, but inflation could have started slightly later, might not have been a constant rate, and the ending was probably not abrupt, although it probably ended by 10 to the minus 32 seconds. So my graph and calculation are only a rough representation because I used a single condition, whereas multiple conditions are possible. Admittedly, cosmic inflation is itself a special condition that cosmologists are assuming, but it replaces three separate special conditions for horizon, flatness, and monopoles. I believe that cosmic inflation is generally widely accepted among cosmologists, but it is still considered speculative. There is indirect evidence for inflation, but not direct evidence. Cosmologists have different models for the timing, magnitude, and ending of inflation. This graph shows, for our proposed idealized scenario, the scale factor, the green curve, for the first 10 to the minus 20th of a second after the Big Bang. The horizontal scale is the logarithm of time in seconds since the Big Bang, from minus 50 on the left to minus 20 on the right. The vertical scale is the logarithm of the scale factor, from minus 60 at the bottom to minus 20 at the top. So, at least 26 orders of magnitude of accelerating exponential expansion in as little as 10 to the minus 34 seconds before the 26 orders of magnitude of decelerating expansion from the end of this inflation until dark energy started to accelerate expansion 6.1 billion years ago. Physicists have theories how this cosmic inflation could have occurred. Relevant terms are inflaton field and false vacuum. The inflaton, not inflation, field turns on with the symmetry breaking of the strong nuclear force separating from the electroweak force at 10 to the minus 36 seconds. So they had been unified, grand unified, and then there was a symmetry breaking and the two split, the strong force and the electroweak force, at 10 to the minus 36 seconds. The inflaton field turns on. The inflaton field has constant energy density, not constant total energy, just as dark energy does. Domination of expansion shifts from radiation to inflaton field energy, and expansion becomes exponential. Expansion shifts from decelerating to accelerating, which is key. Exponential expansion continues for at least 26 orders of magnitude and then stops. Afterward, there is no inflaton field or inflaton particles to be detected or measured. It might seem contrived, wishful, or magical, but physicists have reasons why such a field could have existed, and inflation worked this way. As far as I know, there is no direct evidence for or against cosmic inflation, but there is good indirect evidence from Planck satellite data, and cosmologists are seeking stronger confirmation in cosmic microwave background polarization measurements, B modes. Cosmic inflation solves those three problems, as we will cover. The exponential expansion of cosmic inflation is similar to the exponential expansion our universe will experience in the future due to dark energy, except that the constant energy density of the inflaton field was about 10 to the 27 times the constant energy density of dark energy. And cosmic inflation ended, whereas dark energy density presumably will not end. How does cosmic inflation solve the magnetic monopole problem? No new topological defects were created after the strong nuclear force and the electroweak interaction had separated, so after 10 to the minus 36 seconds after the Big Bang or Planck time. At the start of cosmic inflation, theoretical physicists expect there to have been one topological defect per cosmic particle horizon volume at that time. The scale factor increased rapidly with time, but without cosmic inflation, the cosmic particle horizon distance increased much faster than the scale factor. Without cosmic inflation, there would be something like 3 by 10 to the 78 topological defects within our present cosmic particle horizon volume, and they would have been the dominant energy density from 10 to the minus 16 seconds. If inflation was about 2 by 10 to the 26th, the number density of topological defects would be reduced to about one topological defect in our present, now larger, inflated, observable universe, and perhaps none in our present visible universe. Likewise, for our future observable universe with exponential expansion. After cosmic inflation, topological defect energy density never dominated expansion, and they are not detectable in our visible universe. How does cosmic inflation solve the flatness problem? When radiation or matter dominates expansion, and expansion is decelerating, the flatness deviation increases with time. When expansion is accelerating and exponential, the flatness deviation decreases with time. This is the key. If cosmic inflation was 26 orders of magnitude, then it rapidly reduced the initial flatness deviation by a factor of 10 to the 26th squared equal 10 to the 52, 52 being twice 26, from before inflation to after inflation. After inflation, with radiation and matter dominating expansion, expanding but decelerating, the flatness deviation increased again over time, slowly but relentlessly, by a factor of about 10 to the 51, until now it is less than 0.005 or so. If we need to accommodate a larger initial flatness deviation, we need only increase the amount of cosmic inflation, for example, to 28 orders of magnitude. So our universe could have had significant initial flatness deviation, but it could have been strongly curved, and cosmic inflation flattened out the curvature to give our presently small flatness deviation. If our universe was exactly flat initially, then it is exactly flat today, whether there was cosmic inflation or not. Cosmic inflation does no harm when present curvature is close to flat and could be flat. But it would be a problem if our present universe had substantial curvature. Before inflation, space might have been quite curved and perhaps destined for a positive curvature big crunch, but the curvature became extremely diluted by the huge exponential inflation, so curvature now seems zero or close to it, and our future will be big chill or big rip, even if our universe is finite with small positive curvature. Dark energy density is now higher than the curvature density term, and big crunch will not be our future. How does cosmic inflation solve the horizon problem? With cosmic inflation, our present observable universe that was in causal contact before inflation became at least 7.9 times the size of our present visible universe of the cosmic microwave background, because inflation expanded it. Opposite points of the present visible universe were in causal contact before inflation and might have reached thermal equilibrium at least for gravitational waves. Whatever elementary particles existed at that early time were presumably an opaque relativistic plasma, and I don't know that physics. Nevertheless, cosmologists propose that cosmic inflation is why our cosmic microwave background is so uniform and our universe of galaxy superclusters and cosmic voids seems so uniform on the largest scale. If you watch supplemental video number 4, the cosmic particle horizon distance is this particular integral over time of 1 over the scale factor function of time. Say we had 26 orders of magnitude of exponential inflation starting soon after the grand unification Guth symmetry breaking at 10 to the minus 36 seconds and finishing abruptly at 10 to the minus 34 seconds, just as an example. The scale factor today is still 1 by definition. Scale factors after inflation are unchanged, but the scale factors before inflation become 10 to the 26 times smaller. The scale factor in the denominator of the integrand becomes 10 to the 26 times smaller before inflation starts. So the integrand becomes 10 to the 26 times larger. The horizon distance immediately after inflation becomes 10 to the 26 times larger compared to no inflation. This is good enough for our purposes. We will gloss over the period between start and end of inflation. By the time of last scattering, the horizon distance would have been about 340 times larger than it would have been without inflation, and opposite points on the last scattering surface would have been in causal contact prior to inflation. Horizon distance at last scattering increased from 0.257 megaparsecs to 87.4 megaparsecs with inflation. In this diagram, the opposing points on the dotted circle, here and here, are all within one another's particle horizon observable universes at last scattering time, with our assumed 26 orders of magnitude of inflation. If you're interested in the calculation, see supplemental video number 9. Cosmic inflation would have inflated our present cosmic particle horizon distance by a factor of about 7.7 for 26 orders of magnitude of inflation. So 14,200 megaparsecs without inflation becomes 109,000 megaparsecs with inflation. The present observable universes are shown as the solid circles. Better numbers would depend on the exact amount of inflation, the starting and ending time, and details of how inflation starts and ends. The cosmic microwave background visible horizon distance is unchanged at 13,900 megaparsecs. The present visible universes are shown as the dashed circles. The cosmic particle horizon distance is smaller at earlier times, around twice the speed of light times the time, either for no cosmic inflation or before cosmic inflation. Suppose that astronomers succeeded in detecting cosmic relic neutrinos from the first second after the Big Bang, and are able to determine the neutrino temperature in different directions. Cosmic inflation of 26 orders of magnitude would make the neutrino temperature pretty uniform in all directions. If it turns out not to be very uniform, that could be a problem. Clarifying horizon distance with cosmic inflation. But now we need to clarify the terms horizon distance and observable universe. In this course, up to this point, I have used observable universe to mean the region of the universe from which we could potentially have received a signal emitted after the Planck time, assuming there was no cosmic inflation. Similarly, for cosmic particle horizon distance, 14,200 megaparsecs. We imagine the signal as being a gravitational wave since the universe was opaque to all other particles prior to neutrino decoupling at 1 second. These values would be essentially the same as taking the signal as starting shortly after cosmic inflation. So, for example, the present neutrino horizon distance. But with cosmic inflation, our actual cosmic particle horizon for causal contact, presumed thermal equilibrium, and gravitational wave signals emitted before cosmic inflation is now at least 7.7 times larger, 109,000 megaparsecs, due to cosmic inflation, as is the observable universe. This is how cosmic inflation solves the horizon problem for the cosmic microwave background. So now, when you see a number for the cosmic particle horizon, you need the context of whether cosmic inflation is assumed or not, and how much inflation is assumed. More inflation produces a larger particle horizon distance and larger observable universe. The size of the visible universe is unchanged because the cosmic microwave signals were emitted long after cosmic inflation. Our use of visible universe for the CMB is fine and unchanged. Of course, we don't need cosmic inflation if our universe's initial state was almost perfectly uniform in energy density and temperature, with very specific infinitesimal fluctuations, and the universe has always been infinite in extent with exactly zero curvature, flat, and the universe never created any magnetic monopoles or other topological defects. But now we have a possible solution to explain the universe we see without assuming these three special conditions, replacing them with cosmic inflation as one special condition. Cosmic reheating. Radiation temperature falls with expansion. So why was our universe not extremely cold and devoid of particles after cosmic inflation? Cosmologists believe that the energy accumulated in the inflaton field was returned to radiation particles in a process called cosmic reheating, such that the temperature was as hot immediately after cosmic inflation as before inflation. So we look back to see a hot Big Bang. I initially assumed that during cosmic inflation, radiation temperature would fall inversely with scale factors, so by a factor of at least 10 to the 26 before reheating. But Wikipedia says cosmic inflation is a period of supercooled expansion and temperature only falls by a factor of 10 to the 5 or so initially, then remains constant during inflation, and finally reheats to the pre-inflationary temperature. I don't know the physics here. Particle densities plummeted to near zero during cosmic inflation, which is how the magnetic monopole problem got solved. When inflation completed, reheating caused particle pairs to be created to repopulate the universe to the pre-inflationary densities and temperature, except that magnetic monopoles and other topological defects could not be created after cosmic inflation, and their density had diluted to near zero. Confusingly, some authors called the time of reheating the hot Big Bang, and the inflation was before the Big Bang. Cosmic inflation is speculative, so I tend to think of the end of reheating as more trusted and less speculative, but I don't say before the Big Bang to mean before inflation. Switching back to the present. About 3.6 billion years ago, the matter and radiation energy density fell below the dark energy density, and since then the dark energy density has dominated the expansion of the universe, which has been accelerating. In the future, expansion will approach an exponential function of time, and the scale factor will increase by a factor of 10 every 40 billion years. But in the extremely early universe, one scenario has the exponential expansion increasing the scale factor by a factor of 10 every 5 by 10 to the minus 36 seconds or so, and continue to increase the scale factor by at least 26 orders of magnitude. That was an amazing epoch of the expansion of the universe, if true. These amounts of time are too small for us to really appreciate, but there is a different way to look at this, relative to the extremely small Planck time. If there was inflation, it may have started between 20 million and 200 million Planck times after the Big Bang. Then inflation continued for at least 60 to 130 times longer than the starting time. Then inflation ended, reheating occurred, particle pairs were created and repopulated the universe, and expansion went back to being dominated by radiation. So when inflation ended, the universe had been undergoing exponential inflation for 98% of its existence, if true. This is a link to an article a related article that you might find interesting. We cover more about the conditions in this early period in the next section. The rest of this video discusses those cosmic microwave background temperature fluctuations from the standpoint of cosmic inflation. If this does not interest you, skip to the next video. Cosmologists attribute the small but non-zero differences in the cosmic microwave background temperature in different directions to small magnitude overdensities and underdensities of dark matter at different size scales across our particular last scattering surface at the time of last scattering, 370,000 years after the Big Bang. Two directions in the sky, separated by 1.1 degrees or more, could not have been in causal contact to have nearly the same temperature if radiation dominated expansion in the first 10 to the minus 33 seconds after the Big Bang or Planck time, and there had been no cosmic inflation. But now we have learned about cosmic inflation. Consider dividing the Planck CMB map into 40,000 equal small regions that were never in causal contact with one another, and yet their temperatures agree to 30 parts per million. Not exactly equal, but only small differences. Cosmic inflation is the way for those regions to have been causally connected before inflation. We can also think about the CMB fluctuations with small angular size. The magnitudes of those dark matter overdensities and underdensities increased with time when expansion was dominated by matter or radiation, so decelerating. Working backward in time, the standard cosmological model says that matter and energy density should have been much more isotropic at 10 to the minus 33 seconds after the Big Bang than at last scattering. During exponential cosmic inflation, energy density fluctuations keep a constant fractional amplitude. Cosmologists say that the inflaton field would have had quantum fluctuations of the right magnitude to leave fluctuations in reheated radiation energy density after inflation that would later produce the initial fluctuations in dark matter density that would later produce the fluctuations of the cosmic microwave background temperatures that we see. The physics of the inflaton field and its fluctuations are beyond my understanding. However, this does have the advantage of not relying on quantum fluctuations at the Planck time, when general relativity is not valid. It's complicated, but I can give one rough number. Let's say that some overdensity region that will eventually become a galaxy supercluster is 10 parts per million overdense at last scattering. The overdensity is perhaps 94 parts per billion 1 second after the Big Bang, and 26 parts per billion 10 to the minus 32 seconds after the Big Bang. Presumably, this is within the inflaton field fluctuations, but I don't know. This completes the material on cosmic inflation. To see what was happening with elementary particles in the early universe, continue with the next section.